Good afternoon, everyone, and welcome to this week's Brown Bag Launch Seminar. And today, we are pleased to have two students to present this week. And the first presenter is Jishnu Medisetti. He is a fourth-year undergraduate student in our school, and he's graduating this year. And he will be continuing with his master degree in spring 2020. He is currently working in Dr. Glenn Lance's research group, and he has also worked at Dr. Koki Ko's research group last semester. His interest in mission operations, and that is also the topic of his presentation today. Okay, now let's welcome Jishnu to give us the presentation. And for the rest of you, and please mute yourself do and not interrupt his presentation, and you can keep the question at the end, and we will have a Q&A session. Thank you very much.
All right, thank you, Dr. Sun. Hello, everyone. My name is Jishnu Medisetti, and today we are going to be talking about the conceptual design and data visualizations for the Georgia Tech Mission Operations and Control Center, or the GTMOCC. All right. So here's a quick overview of how my presentation is going to go. First, I'm going to talk about what is a MOCC, and then talk about the current state of what we have in terms of a ground station and mission control, and then give a brief overview of how our data is going to be handled and processed, and then go into detail of the different visualizations that we have. And then I have a quick demo of all of this put together so you can see what happens from when we receive a transmission from a satellite all the way to when it gets presented. And then go over the different operating modes, and then finally end with some of the future developments that we are looking forward to implementing later in the semester. All right, so what is a MOCC? So the MOCC stands for Mission Operations and Control Center. And so this is basically where all the non-science operations of a mission are conducted. And this can include analyzing and displaying critical telemetry, along with preparing to send commands to a spacecraft. So the purpose of the Georgia Tech MOCC is to handle all the operations for SSDL satellites in-house. So there's a lot of Cubesat missions that we have planned in the near future. GT1, in fact, is launching this spring. And then we have TARGIT from Dr. Gunter's lab, along with some larger missions planned in the future, including SWARM-EX and VISORS. And so we want to be able to do all the mission operations for these satellites in our own facilities. We also want to leave the possibility open for other universities to use their ground station and MOCC for their own operations in the future. Right. Oh, there it is. Okay. All right, so here's the current state of what we have for the Mission Control Center. So we have 3 different ground stations at Georgia Tech. We have the Montgomery Knight UHF antenna. We also have the one on top of Van Leer, which does UHF and VHF. And we also have the GTRI Cobb County Research Facility, which has an S-band antenna. Now, out of the 3 of these, the one on top of Montgomery Knight is the only one that's currently operational. And whenever we receive telemetry, it stores it locally on its own computer. And we use the clearinghouse software to act as a router and server for the data. And we have the Quantum CMD program in order to visualize this data and send commands to our satellites. And then we also have our mission control room on ESM 301. Now, this is where we want to centralize all our operations. So instead of having 3 separate ground stations with their own computers in 3 different locations, we want to connect them all to the facility in ESM 301 and make that the central control room where we display all our visualizations and do all of our satellite commands. All right. So here is the proposed layout of how data will be handled from the satellite once we establish a link. So if we have a satellite that's passing overhead currently, one of our 3 ground stations is going to pick up that signal and process it. And that live data is going to be sent directly to our MOCC. Now, the data that we get from these satellites can vary depending on the mission and the satellite and a whole lot of other things. And so, but 2 of the general data sets that we're probably going to get include the satellite health status. So that includes things like your battery charge, how much power your solar panels are generating, what the thermals of your different subsystems look like, etc. and then the location data, which is gathered by the GPS, if the satellite has a GPS. Now, the data format that this location data can be in, again, varies depending on the satellite and the mission. But for the sake of this example, I'm going to assume that it's in the form of a TLE, which I'll explain later on in the presentation. So once we get our position data, we have to process it a little further. So we're going to convert our TLEs into orbital elements to understand the orbit of our satellite. And then from there, we update the propagation on the central STK scenario. So STK is a program that lets us visualize and propagate satellite orbits. And using that visualization, we can create the ground track for our satellite, along with the 3D plot showing the Earth and the orbits of our satellite going around it. And this will get directly fed into our TV displays inside the MOCC. From SDK, we can also compute something called access. And what access lets us figure out is what the time intervals are where our ground station antennas can pick up our satellite. So when is this going to happen and for how long? And that's really important for scheduling passes and also for some of our other visualizations. And these get fed, again, directly to our TV display. Our satellite health gets fed directly to our health status display apps. All right. So a quick overview of what a TLE is. So a TLE, or two-line element, is a standard format set by NORAD, which identifies the mean orbital elements for an Earth orbiting satellite. So as you can see in this figure over here, every satellite has 6 orbital elements, which define the geometry of its orbit along with its location along its orbit. So these include the semi-major axis, your eccentricity, the inclination angle, the right ascension of the ascending node, or the RON, the argument of perigee, and finally your true anomaly. So the TLE itself is given in this format here, as you can see in the bottom picture, where the second line gives us 4 out of our 6 orbital elements. The other 2 can be calculated using these equations. So our semi-major axis A is calculated using nu, which is the mean motion given by our TLE, and mu, which is the gravitational parameter of the Earth. Our true anomaly is a little bit more complicated. You use the mean anomaly given by our TLE and solve Kepler's equation for a geometric parameter E. And this is done using a numerical method like Newton iteration. And once we get E, we plug that into this equation here to solve for our true anomaly F. All right, and so we take all these orbital elements and we put them into our STK scenario. So this is what our STK scenario looks like. So on our our left, we have the 3D plot showing the Earth, along with the propagated orbits of each of our satellites and their current locations. And this can be played in real time or at any speed that we want, along with the location of our ground stations. Now, on our right, we have the ground track that these satellites create, and this is propagated for 1 orbit interval. And we can also see our ground station here. So we can input our new orbital parameters. So every time a satellite passes overhead, we have its last known location, right? And we take that location data and we can put it into STK for it to recalculate the new trajectory of the satellite. And it can do this in a variety of different methods, including a very simple 2-body plot assumption, all the way up to accounting for different perturbations like the J2 perturbation. And so this allows us to get the most accurate representation of where our satellite is located at any moment. All right. So here are some of the proposed visualizations that we have. First of all, we have our sky plots, which is a polar plot of the satellite's pass in the sky, centered around the ground station at the center of the polar plot. And so this is useful for our satellites to point their azimuth and elevation angle in order to establish the best link they can with the satellite. Now, this data is generated directly by the ground station software itself. And however, our MATLAB apps are actually pulling this data from our SDK scenario. Once we establish the link between our mission control center and our ground station, we'll be able to pull this directly from our ground station instead. We also have this data table here, which shows the next 3 expected passes for the satellite overhead. So we'll know what satellite's going to pass and the time interval of when it's going to occur. After that, we have our ground station app over here. And our ground station app shows each of our antennas and when their next expected pass is going to occur overhead. And usually these antennas are actually colored in gray, and when an active pass is happening, that antenna will light up in green and the downlink frequency will be displayed overhead. Now, along with this, we're also going to be displaying waterfall plots, as you can see here, and this shows the different signal frequencies that we're receiving. And this is taken directly from the ground station antenna itself, along with our health status apps, which are not shown here yet, but those show different things, again, like battery charge, the temperature in your different subsystems, and how much power your solar panels are generating. All right, so here is a quick demo so you can kind of see how all of this is put together. So here we have our SDK scenario, as you can see on the right, or on the left. And this figure over here that I'm rotating, that's our 3D plot showing the different propagated orbits for each of our satellites, along with our ground station. And then on the left over here, we also have our satellite ground track. And so that shows the satellite on a 2D map over the Earth. Now, when we receive a transmission from a satellite, so I've already queued up a new TLE. Now, obviously, this has been pre-recorded, so this isn't a live transmission, and it's just an example. But I have the TLE ready to go. And when I press run on the script, as you can see in a second, the position of the satellite's orbits have changed, right? Now, this is a very drastic change. Normally, these satellites perturb by a very small amount, and so it won't be this drastic. But for the sake of demonstration, I changed the inclination angles by a large amount, so you can see. Now, after this, we can compute our axis for the satellite. And so when we do that, it'll tell us when our ground station is going to be able to see the satellite in the sky. And once we have that data, we can run through and generate our different display apps. So our first one here is going to be our table update app. So give it a minute. And here we go. So this shows us the next 3 expected satellites we're going to see overhead, including the time intervals in which we'll see them. So we have range B is going to pass overhead 2 times, and then prox 1. And I ran this morning, so you can see these are up-to-date values. Next, we have our ground station app. And so this ground station app tells us that we're going to have a pass over Montgomery night in the next 24 minutes from the time that I took this video. And when we have that pass, it'll light up in green, and we'll see its frequency information. And currently, the Van Leer and GTRI satellite ground stations are not put into our program yet, so we don't have data from them. And then lastly, we have our polar plots. So once this opens up, here we go. So we can see the polar plots of our different satellites. So we have range B and prox 1. And so we can see where it looks like in the sky as they pass overhead, along with the time interval and their maximum elevation. Now, this polar plot will be generated live as our satellite passes going overhead, so you can see where the satellite is. All right. So now let's talk about our different operating modes. So we have 3 different operating modes for the MOCC, and in each of these modes, what we display on our TVs and the different activities that occur change. And so first we have our pre-pass phase. And this is the nominal condition where we don't have a pass currently occurring. And during this time, our displays are going to show our satellite pass data table, the ground station app, and our STK scenario is going to show our ground track and 3D plot with all the satellites visible. And this is also the time when an ops team can queue up commands to send to the satellite when a pass is about to happen. And then during the pass, we're going to establish the live link between the MOCC and the ground station, and all the queued up commands are going to be sent. Along with this, our ground station app and our Skyfall, our Skyplot and Waterfall apps are also going to be presented live. And the STK scenario is going to hide all the other satellites except for the one that we're currently visualizing. And we're also going to display the health status of the current satellite. And then finally, once the pass has ended and up to an hour afterwards, we are going to show the final sky plots and waterfall plot from the pass that just occurred. And the SDK model is going to update to represent the new orbits of these satellites, along with the rest of the satellites are going to come back into view. All right, so finally, here's some of the future developments that we expect to see upcoming. And so first of all, as the GTMOCC develops, there's a lot of ideas and functionalities we want to implement. So first of all, the display apps are going to be finalized and coded up, and a script is going to be created to automate the cycling between the different operating modes. So currently this is done manually, but ideally we would like it to happen on its own when we expect to see a pass. And then the biggest thing is to establish the ground station network between the connection between our ground station and our MOCC. And this will allow us to get live time data as well as be able to send commands directly up to the satellite. And then lastly, we want to establish the clearinghouse network to connect our ground station to other universities. And this will allow us to be part of a larger link. And so when other ground station communities want to use our antennas or our MOCC, they're able to log onto the network and use our facilities. All right. So that's the end of my presentation. And do any of you guys have questions?
Yeah, I have a question.
Yeah, please go ahead.
So what type of data do you guys, well, firstly, very awesome presentation. What type of data do you guys get from the CubeSats that you have in orbit?
Yeah, so you can get, again, so that really depends on the satellite itself, right? In every mission, every satellite has its own capabilities. So if the satellite has a GPS on it, we'll be able to get location data. So we'll know things like its current position and velocity vector. Or, and commonly we'll get things like the battery status of your satellite, the different thermal temperatures inside. It really just depends on the capabilities of the satellite itself. So that really depends on the team that's made it.
Is there any other questions?
Yeah, I've got a quick question. Really enjoyed your presentation. I was wondering, are you looking for other people to help get involved? And if people were interested and wanted to help contribute, what would be the ways that we could do?
Yeah, definitely. So currently the mission operations team is working under Dr. Lightsey in the Glenn Lightsey Research Group. So if this is something you're interested in, something that that you would like to do, the best thing to do would be to email and talk to Dr. Lightsey and see if he has any open positions in his lab for undergraduate research.
Thanks.
Yep.
All right, thank you very much for sharing your research and experience with us. And are there any other questions from the audience? Okay, if not, let's thank Jishnu. Pavan, can you start to share your screen?
Yeah, I can start sharing my screen.
Okay, perfect. Right. Okay, everybody, and in the following, we will have Pavan Patel and to present for us. He is currently a senior undergraduate student in our school. He has been working with Professor Suresh Menon in the Computational Combustion Lab since the spring of 2019. His interest lies in the propulsion and combustion physics, and today he will present his recent work on numerical simulation of reacting flow in a 7-injector gas, methane, and a GOX rocket engine.
All right. Thank you, Professor Sun. Before I begin, I'd just like to thank Professor Menon for all the guidance and support, and also I'd like to thank Shubham, Mark, Achyut for their support, help, and of course Principio and Matt, without whom this wouldn't be possible. All right, so to begin, I think let me see one way. We know that going to space is very expensive. One way we can reduce the cost of going to space is if we use less propellant for our launch vehicles, and if we can reduce the propellant, we can reduce the cost. One way we can reduce the propellant is if we change our propellants to something like methane, and methane has many advantages over hydrogen and RP1. And they're listed here, but although the ISP of hydrogen is much higher, the overall benefits of using methane are significantly better or significantly higher. But to design methane-fueled rocket engines, we really need to understand the physics inside the combustion chamber, and doing that is really expensive experimentally. So one of the options is to use numerical simulations, because in numerical simulations you can explore the physics and combustion processes involved. So in this presentation, I'll be showing the numerical simulation that we did in the lab of an experimental rocket engine, and I'll focus mostly on the flow features and the flame structure. So this is the experimental rig. It was developed at TUM. It has 7 injectors that are flushed right at the faceplate, and there is no recess. And this is the combustion chamber. There is the important thing to note here is that the walls are cooled by water, so there is heat flux going through the wall, and these are the geometrical features. And so we developed a grid that was just like this, that mimics this experimental rig, and it looks something like this. Now, the important difference between the experiment and what we did is the wall here is adiabatic. The experimental walls are not adiabatic, as I mentioned. They have heat flux. But here we are using an adiabatic wall. Now, this is a little snapshot of the grid that we used. It extends out further. We are solving the full domain of the combustion chamber, and there are about 21.4 million cells in the whole domain. This is a picture of the faceplate, and in most of the contour plots that I'll be showing, there'll be slices cutting through these 3 injectors, or a slice cutting the single injector in the middle like this in the normal to the Y direction. The blue region here is where the oxygen is coming out from, and the red fuel sleeve is for methane. And the region in between, the gray region, is the GOX post. And these are the flow conditions, and the geometry is exactly like the experiment. But these are the flow conditions, and the important parameter here is the mixture ratio, which is quite lean, 2.65. It's a lean mixture. So continue with the numerical setup. As I mentioned, we're doing an LES CFD simulation. And for LES, the grid you use is very important. The grid here is quite fine. For example, this is an injector, a very close-up view of the injector. And you can see this is the GOX post, and the shear layer is going to be around here. And there are very high species gradients across this shear layer that you will see in the coming slides. And it's very important to capture them. So your grid needs to be good enough, and it needs to be fine enough for an LES study. And one way to verify whether your grid is good for an LES study is to look at the turbulent kinetic energy, which shows the minus 5/3 Kolmogorov slope, which is a way to verify the the validity of the grid. We're using a two-step 6-species kinetic mechanism, and we have run it in this, the simulation I'm showing here. It was run for 6 milliseconds, which is about 12 flow-through times, and it used 1600 processors. And to run for 6 milliseconds, the simulation took 4 days to complete, about 4 days. And something important that I forgot to mention is we're assuming a thermally perfect gas, and we are also using the one equation KSGS model for subgrid kinetic energy. All right, so let's begin with the flame characteristics. The flame is anchored at the GOX post, and it's important that the flame is anchored at the GOX post so that we have stable combustion. Another thing we noticed is the flames are wrinkled. This wrinkling is due to the turbulent shear layer, and we'll see that again in the coming slides. This turbulent shear layer is also spreading the flame in this transverse direction. And this, by the way, is a slice of the 3 injectors here, and it's normal to the Y plane. And it's not the full chamber, it's just a little piece of the slice also. And yeah, and these pink lines here, they represent the stoichiometric mixture fraction. So to really understand the coherent flame structure, you would want to take the time average of this reacting flow. And if you take the time average of the temperature field, this is what you'll see. And this black contour lines, again, represent the stoichiometric mixture fraction. And we can see here that, as we mentioned, the flame is expanding. It's spreading in the transverse direction, and it's going towards the wall. And the mixture fraction is not that high to keep the flame from going there. Because the mixture fraction is 2.65, the methane jet velocity is good enough to push the flame towards the wall. And because it pushes the flame towards the wall very early on, the temperatures at the wall are very high, as you can see in the plot to the left. Another important thing to mention is that, so these are the injectors, these 3 injectors here, and the flames between the flames of each of the injectors are interacting, especially in this region. You can see that the flame of this injector is interacting with the flame of this injector. And this interaction is not a problem if you have stable combustion, but if for example, maybe this flame was to lift off, it would perturb the flame here because it's interacting with it, and that could perturb this flame or this flame, and it could move from stable combustion to unstable combustion, and that is not something that is desired inside the combustion chamber. So if we look further into the flame through the reaction rate, we can see that the instantaneous snapshot of the reaction rate shows us the shear layer. And this is a very turbulent shear layer, as you can see. And it's because of their very small scale turbulent vortices within the shear layer that are stretching the shear layer, stretching or shrinking and the shear layer, and that also plays a role in shaping the flame, the coherent structure of the flame. And if you take a mean of all a time average of the reaction rate, we can see that the reaction layer is quite thick, around 0.01 meters also. And this is the reason why the flame expands also. All right, so another way we can characterize the flame is through the flame index. And the flame index shown here is pretty much the Takino flame index, which is this. But here I've multiplied the reaction rate of fuel so that we're only looking at the regions where there is burning, where there is some kind of burning. And the thing with the flame index is that if you have a negative flame index, that means that you're burning in a diffusion mode. And if you have a positive flame index, you're burning in a premixed mode. So from here, we can see that there's a lot of blue, and that represents a negative flame index, which means the flames are quite are diffusive. And that's kind of obvious because we're not mixing the fuel and oxidizer prior to combustion, and there's also no recess. The fuel and oxidizer both enter the chamber at the same time in the same location. So that's one thing we can see. The flames are predominantly diffusion, but that doesn't mean they're only diffusion. You can see some premixed burning going on here and there, and but most of it is diffusion flame. Something I quickly wanted to show is the O2 reaction rate. Initially upstream, we have oxygen being consumed, and as you go downstream, after the products have been formed, we have oxygen being produced because of this two-step kinetic mechanism we're using. In the second step, the second reaction is reversible. So CO2 that is produced at the end of combustion, some of that CO2 is being dissociated into carbon monoxide and oxygen, and some of that oxygen is being produced. And the red dots you see as you go downstream, it represents the rate at which the oxygen is being produced. It's not a lot, but it's there. And so if we look at the overall mass fractions of the major species involved, which is a fuel here, the CH4, the oxygen, carbon monoxide, H2O, and CO2, we can see that in the fuel, there is some unburned fuel at the walls of this chamber, and it may not be very clear here, but there is some fuel exiting the rocket engine, which is not something which is not really very good, because CH4 absorbs a lot of heat, and that's not really good for the environment. Similarly, with the carbon monoxide, you can see unburnt carbon monoxide is leaving the chamber and also the engine, which is not really good for the environment. But O2, H2O, and CO2, most of it is in the core, unlike the CH4 and CO. And it's O2 and H2O is fine. CO2 is it's harmful for the environment, but it is a combustion product. So, ideally you'd want to use up all your fuel and make sure there's also no carbon dioxide. Now, if we shift our focus to the fluid mechanics side of the flow, we can look at the recirculation zone inside the chamber. The recirculation zone it varies azimuthally. So if you look at this contour plot at the bottom right, it has high vorticities between the injectors, but a low vorticity right above or below the injectors. And if we take a slice through these three injectors and we plot the stream trace through it, we can see that there's a recirculation zone that is small. There's a small recirculation zone. The rotation is small. The vortices are small, and so the vorticity is small. And on the other hand, if we take a slice in the z direction, in the y direction, normal to z, we will see that the recirculation zone is much larger, and the vorticity also is much larger. So we are seeing that the recirculation zone varies azimuthally. But the interesting thing to note here is that although the recirculation zone size varies, the reattachment point, which is here at about 0.01, is the same in both cases. And also here it's 0.01. And the effect of this reattachment point is one of the ways they quantify the recirculation zone, and it has an effect on the pressure profile, and the pressure profile is what we're going to talk about next. It is very important how the recirculation zone shows up in the pressure profile. So this is pressure. Pressure is, by the way, one of the most important properties inside a rocket engine. The pressure profile, the axial pressure profile, can tell you a lot about what's happening inside the rocket engine. Okay, now here we see that the CFD underpredicts what the experimental group has shown, and it underpredicts it by 1 bar. But you gotta remember that the experimental wall had heat flux. It was an isothermal wall, while the CFD wall the wall we used in our CFD simulation had a boundary condition which made it adiabatic. So the heat flux kind of affects the pressure. Here we don't have any heat flux, and so that's the reason why there's a difference. So it's not really an apples to apples comparison, but I put it here to show that the general trend of pressure is fairly captured, as you can see in this plot. And what this pressure profile is telling us is that, okay, basically what's happening is we have a little spike in pressure and then a steep drop in pressure and then a gradual drop. So this little spike here is because of that recirculation zone we saw earlier. And if you see, the location of this spike is at about 10 mm, which is also where the reattachment point was for the recirculation after the recirculation zone. So the recirculation zone kind of increases the pressure near the wall. And then because of combustion, we have this steep pressure drop. And what happens is the heat release due to combustion accelerates the flow. And that acceleration increases the velocity. And because the velocity goes up, the pressure goes down. So how quickly it combusts is how quickly heat is released. So if you have a very quick mixing and very quick combustion, this is going to get steeper and steeper. If your mixing is happening much further downstream, this is going to this slope is going to be a little more gentle. And then once combustion is complete, you'll see an inflection point here, and around here we can see that. And that's because there's no more heat release, or if there is, it's very little. And then after that, the pressure kind of tries to plateau. And we can see that happening here. There is a gradual decrease, maybe because we still have some heat release here and there inside the chamber. And the important thing here is that if you want to have a high exit velocity, which is important to reduce the amount of propellant you take, you want to make sure the pressure as you approach this nozzle is as high as possible. And if you want it as high as possible, you want to make sure this slope here is not very steep. You want to make it as gentle as possible. So you want to make sure there's mixing happening and then combustion is happening much later, further downstream. That way your gradual pressure drop is not as much, and so you can increase your exit velocity and therefore your ISP. And to do that, really, what the experimental group found was that when they increased the oxygen to fuel ratio, this slope became a little more gentle. So moved the mixture much further downstream. And here we're seeing that combustion ends at about 100 mm, while the experimental group says their combustion ends at about 150 mm. And this is fair, I guess, because we have an adiabatic wall, and we are not sure exactly how that would affect this pressure profile and where combustion ends and the location at which combustion ends. So this is pressure, just the pressure profile, and its pressure profile is really important to kind of validate your numerical study. If you can match the pressure profiles, you can really tell what's happening inside the chamber very well, and you can explore what the experimental group probably couldn't find because they cannot put probes at every place in the chamber. And something that's important is also the pressure fluctuation. The pressure fluctuation is important because if you have a lot of instability, you can damage the chamber, and the integrity of the assembly. And when that happens, you cannot really reuse your engine. And if you want to save costs, you want to make sure you can reuse the methane fuel, the rocket engine. And so you want to make sure you don't have a lot of very high pressure oscillations. Though here we do see pressure oscillations, they're not that high. For example, this is the trace of pressure, and in this pressure trace indicates the combustion roughness, by the way. And here we can see that the pressure fluctuations are between plus 2.5 and minus 2.5%. So this is pretty close to what the experimental group also observed. The experimental group saw a combustion roughness too, and their pressure fluctuations were between 2%, plus or minus 2%, which is quite close to what we are also seeing. And we have very high frequency fluctuations, but they're of a very low amplitude. The high amplitude fluctuations are not very frequent. Here you can see the how pressure fluctuation varies as you go downstream. This point where combustion ends is where we see max pressure fluctuation, but this pressure fluctuation here, the max pressure fluctuation, is still not that high when you consider how high it can get if you had maybe combustion instability or pressure instabilities. And so that is pretty much it. This is what I had to show. I think we identified some of the key flow features and characteristics. We saw how the turbulent diffusion flames in this 7-element rocket engine is, the reaction zone, the reaction zone, recirculation zone, the pressure footprint, and a few other things. But it's important to quantify all these features, and so that we can understand how these features affect some of the important aspects of a rocket engine, such as wall heat transfer and the engine performance, or the exit velocity and ISP and that kind of stuff. But wall heat transfer is quite important because we want to know how much, if you have a regeneratively cooled rocket engine, you want to know how much temperature the fuel coming into the chamber is going to have. And because you're heating the fuel with the heat transfer from the chamber, you want to know exactly what the heat flux is at the wall. So yeah, that's it. And if you have any questions, I'm ready to take them now.
Okay, Pavan, thank you very much. Are there any questions to Pavan? Okay, I didn't hear anything. I have a quick question. When you showed the recirculation, it turns out there is a recirculation at the top boundary and bottom boundary, but I didn't see recirculation between in the center area.
Where?
For the figure on the left.
This one?
Yeah.
Oh, in between here? Are you talking about the recirculation
right.
here? Oh, there is recirculation here. In fact, it's very important there's recirculation here. There's also recirculation at the GOCS post tip, but it's very fine, and it's not shown here because it kind of makes the plot messy and all. But there is recirculation, and it's very important that there's recirculation at the GOCS post, especially to keep the flame anchored.
Right.
You want the flame anchored. Yeah.
Okay, thank you. Any other questions?
Hello, I have a question. Pavan, can you comment on the computational cost of all these simulations? Like how much time it takes and how many processors you have been running this on?
We run it on 1600 processors. It took about 4 days to run 6 milliseconds of the flow. So yeah, it took that's the computational cost was about if I remember correctly, it was about 100,000 CPU hours, a little more than 100,000 CPU hours.
Thank you.
All right. So if there are no other questions, so let's thank Pavan Patel. Thank you very much, and thank everyone attending this week's Brown Backlog seminar.